Yesterday, the seafloor at the edge of Antarctica released two strong earthquakes 11 minutes apart, both magnitude 6, both at the same spot, on a plate boundary that almost nobody has heard of. The Southeast Indian Ridge. 65,000 kilometers of underwater mountain chain that runs through every ocean basin on Earth, the longest mountain range on the planet by far, and almost nobody outside of geology knows it exists. Yesterday, on one segment of that ridge, between Australia and Antarctica, the seafloor cracked twice in the same place. And by the time the second event had been catalogued, a viral framing had already attached itself to the news, claiming that this is evidence the Earth itself is expanding, that the planet is, slowly, growing into a much bigger entity the likes of Jupiter or Saturn, and that the science you were taught in school has been lying to you. Tonight we walk through the actual story, what doublet earthquakes are, why this one happened, and why the viral framing gets the right observation and the wrong conclusion. Before we go any further, if you like what we do here at Project Nightwatch, hit like and subscribe so you do not miss any of our nightly debriefs, and leave a comment with where you're tuning in from tonight. Now let's break this down. Part 1. The same dot. Twice. Yesterday afternoon, at 51 minutes past 2 o'clock in the afternoon Coordinated Universal Time, on the 27th of May, 2026, the United States Geological Survey Catalogue quietly logged a magnitude 6.0 earthquake at the bottom of the Southern Ocean. The location was specific, the depth was specific, the coordinates were specific, latitude 50.46 degrees south, longitude 139.44 degrees east, depth 10 kilometers, no tsunami flag, no human population within 1,000 kilometers. The kind of earthquake that, on any other day, you would mark, you would log, and you would move on from, because the deep ocean produces moderate earthquakes routinely, and the world rarely notices. 10 minutes and 6 seconds later, at 15:01 Coordinated Universal Time, the same catalogue logged a second magnitude 6.0 earthquake. Same depth, 10 kilometers, same latitude, to the 100th of a degree, same longitude to the 100th of a degree, same plate boundary, same fault system, same magnitude, two identical earthquakes, 11 minutes apart, at what is essentially the same dot on the map of the seafloor. If you pull up the USGS earthquake map and you zoom out to the world view, the two events do not even render as separate points. They overlap. They sit on top of each other. The cartographic resolution of the global map is coarser than the actual spatial separation between these two ruptures, which means at the scale most people will ever see this story, they look like a single earthquake that happened twice, which is, in a sense, exactly what it was. This kind of coincidence is so unusual that the first reaction inside the seismological community was the same reaction a lot of viewers had when they saw the catalogue refresh in real time. The reaction was, is this an error? Is the system glitching? Did somebody enter the same event twice? Did the automatic algorithm pick up a phase from one earthquake and incorrectly assign it to a second imaginary earthquake? Because that does happen, every catalogue has spurious entries, every detection algorithm has false positives, and when you see two events with identical magnitude, identical coordinates, and a separation that looks suspicious like a duplicate database row, the first move you make is to question the data. But the data is not the problem. Both events have independent solutions from multiple agencies. The European Mediterranean Seismological Centre logged both events with the same separation, the same depths, and the same magnitudes. The waveforms recorded by the Global Seismic Network show two distinct ruptures, with two distinct onset times, two distinct travel time fingerprints, and two distinct sets of arriving phases at the recording stations on Tasmania, on Macquarie Island, and on the Antarctic coast. These are two real earthquakes, two real ruptures of the seafloor, two real releases of seismic energy. They just happened in a way that is almost designed to make you wonder if you're looking at a glitch. That is what makes this story interesting in the first place. Because the immediate question is no longer where did this happen, or how big was it, or did anyone get hurt? The immediate question is, why did this happen twice? Why did the seafloor rupture twice in the same place, 11 minutes apart at the exact same magnitude? Because earthquakes do not usually do that. Earthquakes have a normal pattern, and this pair does not fit it. Most earthquake sequences follow a shape that has been studied for over 100 years. There is something called Amori's law, which describes how the rate of aftershocks decays over time after a major rupture. Aftershocks happen most frequently in the first hours after a main shock, and the rate falls off roughly with the inverse of time. There is something called Barth's law, which describes the magnitude relationship between a main shock and its largest aftershock. The largest aftershock is typically about 1 magnitude unit smaller than the main shock. If a magnitude 7 happens, the largest aftershock is usually around magnitude 6. If a magnitude 6 happens, the largest aftershock is usually around magnitude 5. The pattern is so reliable that seismologists use it as a rule of thumb to decide whether a sequence is unusual. The doublet yesterday violates Barth's law. The second event is the same magnitude as the first, not 1 unit smaller, not half a unit smaller, the same. To the level of precision that the catalogue reports, the two events are indistinguishable in size. That is not what aftershocks usually look like. The doublet also does not look like a foreshock main shock sequence. In a typical foreshock pattern, you see a smaller event in advance, building the stress, and then a larger event that releases it. The largest earthquakes ever recorded have all had measurable foreshocks in the days or hours before, when you go back and look at the catalogue with the benefit of hindsight. But the smaller then bigger pattern is the rule. Yesterday's event was equal then equal. The first quake was magnitude 6. The second quake was magnitude 6. Neither one was clearly the foreshock or the main shock of the other. What you're left with is the textbook seismological definition of a doublet. 2 earthquakes of comparable magnitude, occurring within a short time interval at essentially the same location. Doublets exist in the global catalogue. They have been documented across a wide range of tectonic settings, from subduction zones to transform faults to continental plate boundaries. But they are statistically rare. Most pairs of earthquakes in the catalogue are either main shock-aftershock sequences obeying Barth's law, or they are separated in time or space by enough that they are clearly independent events. The pair yesterday is rare in all 3 dimensions: rare in time, rare in space, rare in magnitude identity, and that is before you start asking about the location. Part 2. Where this actually happened. The location of the doublet is one of the most remote places on the surface of the planet. 50 degrees south latitude, 139 degrees east longitude. The closest land is the southwest coast of Tasmania, Australia. The closest population centre of any size is Hobart, the capital of Tasmania, which sits about 1,000 kilometres to the north-northeast of the epicentre. The closest scientific research station is the Australian Antarctic Division Base on Macquarie Island, several hundred kilometres to the east. The Antarctic coastline itself is about 2,000 kilometres to the south. Between these distant outposts there is just ocean, cold, deep ocean, some of the most isolated water on Earth. The Southern Ocean here is the gateway between Australia and Antarctica, a stretch of water that the Antarctic circumpolar current sweeps through on its way around the continent. There are no cities on the seafloor. There are no fishing fleets close enough to feel anything. There are no instruments mounted on the ocean bottom near the epicentre. Everything we know about this earthquake comes from seismic stations hundreds or thousands of kilometres away, where the ground motion from the rupture eventually arrived as faint pressure waves, and where computer algorithms reconstructed the source location, the magnitude, and the timing from the arrival patterns. That distance matters, because it changes how precisely we can know what happened. The closer your seismic stations are to an earthquake, the more accurately you can locate the source, the more precisely you can determine the depth, and the more confidence you can put in the magnitude estimate. The further away the stations are, the more your solution depends on assumptions about how seismic waves travel through the Earth's interior, and the more uncertainty creeps into every number. The doublet's reported depth of 10 kilometres is partly a real measurement and partly a default. When the waveform inversion cannot precisely constrain the depth, the United States Geological Survey assigns a value of 10 kilometres as a placeholder. It is the institutional version of saying we know this happened in the upper crust, but we cannot tell you to the kilometre where in the upper crust. The true depth of the 2 ruptures is almost certainly shallow, but it could be anywhere in the upper 5 to 20 kilometres of oceanic crust at this latitude. The magnitudes themselves are reported to a precision of 0.1, but the actual uncertainty around that value is roughly the same size as the precision, which means the 2 events could differ by an amount smaller than the catalogue can resolve, and we would never know. This is not a flaw. This is honest reporting of what is and is not possible to measure from a long way away. The Southern Ocean is one of the least instrumented seismic regions on the planet. The dense networks of seismometers that exist in Japan, in California, in Chile, in Italy, in Iceland, do not exist out here. There is no Southern Ocean equivalent of the KNet or the KNet or the Italian RAN. There is no equivalent of the Shake Alert system. There are scattered stations on land, mostly on the southern Australian coast, on Tasmania, on a few sub-Antarctic islands, and on the Antarctic continent itself. They are the eyes we have, and they are very far away from the event. The point of mentioning all this is not to say the doublet might not have happened. It happened. Both events are well recorded and well confirmed. The point is to ground you in what kind of story this is. This is not a story like a Japan Trench earthquake where the seismometer network is dense enough that you can practically watch the rupture propagate in real time on a fault model. This is a story where the data we have is the best the available instrumentation can give us, and the best is good enough to confirm 2 real earthquakes happened, but not good enough to tell us the rupture history at the millisecond level, or to put the depth to better than a few kilometers, or to tell us the focal mechanism with absolute certainty. There is also a naming question that comes up at the start of any story about this part of the ocean, and it is worth addressing it now so that you understand why different sources are going to call the location different things. The United States Geological Survey labels this part of the world the Western Indian Antarctic Ridge in its seismic region naming convention. That convention was drawn up decades ago, and it reflects the way the global ocean ridge system was understood at the time. But the actual physiographic feature, the ridge as a geographer or a geophysicist working on plate tectonics would call it, is the Southeast Indian Ridge. The Southeast Indian Ridge extends eastward from the Rodriguez Triple Junction in the central Indian Ocean across the gap between Australia and Antarctica and terminates near the Macquarie Triple Junction southeast of New Zealand. The doublet location is on this ridge, near its eastern end, before it transitions into the more complex Macquarie Ridge structure further east. So when you see one news outlet call this the Western Indian Antarctic Ridge and another call it the Southeast Indian Ridge, they are not describing different events. They are using 2 different naming conventions for the same plate boundary. The Southeast Indian Ridge is the more scientifically standard name. The Western Indian Antarctic Ridge is the USGS catalogue label. Both are correct. What this place actually is, regardless of what you call it, is the boundary between 2 of the major tectonic plates that make up the surface of the Earth. To the north of the ridge is the Australian plate, which carries the continent of Australia and a substantial chunk of the Indian Ocean and the Coral Sea and parts of the Pacific. To the south of the ridge is the Antarctic plate, which carries the continent of Antarctica and a wide ring of seafloor surrounding it. These 2 plates are moving apart, slowly, steadily, for tens of millions of years. The ridge is where that motion is happening, and yesterday's earthquakes were 2 snapshots of that motion, releasing some of its accumulated stress. The question now becomes, what does it actually mean for a ridge to be the boundary between 2 plates that are moving apart, and what kind of earthquakes does that produce? Because the answer is not the same kind of earthquake that hits Japan or Sumatra or Chile. It is a completely different mechanism, and that difference is one of the central reasons the doublet behaved the way it did, including the absence of any tsunami threat. Part 3. What a mid-ocean ridge actually is. If you could drain the world's oceans for a moment and look at the bare seafloor, the most striking feature you would see is a chain of underwater mountains that runs through every ocean basin on the planet. The chain is roughly 65,000 kilometers long. It circles the globe like a seam running across a baseball, branching and weaving but always continuous. It rises from the abyssal plains of the deep ocean to mountains a couple of kilometers tall, with a deep central valley running down the middle. This chain is called the Global Mid-Ocean Ridge System, and it is the longest mountain range on Earth by far. The Andes are about 7,000 kilometers long. The Himalayas are about 2,400. The mid-ocean ridge is more than 30 times the length of the Himalayas. It is just hidden underwater, which is why almost nobody who is not a geologist has heard of it. The mid-ocean ridge is the place where new ocean crust is being created. The way it works is that the upper mantle of the Earth, under the ridge, is hot enough that the rock there is partially molten. The molten rock rises toward the surface because it is less dense than the solid rock around it, and when it reaches the seafloor at the ridge axis it spills out, cools rapidly because it is now in contact with cold seawater, and solidifies into new ocean crust. The new crust gets attached to the 2 plates on either side of the ridge, and then those plates move away from each other, slowly, continuously, for as long as the ridge has been active. The new crust at the ridge axis gets pushed outward. The next batch of molten rock rises behind it. That new batch cools and gets attached, and the cycle continues. The result is that the further you go from a ridge, the older the seafloor is. The ocean crust closest to the ridge is young, sometimes only a few thousand years old. The ocean crust at the far edges of an ocean basin, where the seafloor meets a continental margin, can be hundreds of millions of years old. This process is called seafloor spreading, and the discovery of seafloor spreading in the 1960s was one of the foundational moments of modern Earth science. Before the 1960s, geologists knew that the continents had once been joined together in a supercontinent called Pangaea, because the German meteorologist and geophysicist Alfred Wegener had proposed continental drift in 1912, and the fit between the coasts of Africa and South America was hard to ignore. But Wegener could not explain the mechanism. He could not say why the continents would move, or how. It was the discovery of seafloor spreading, of magnetic stripes on the ocean floor running parallel to the ridge axis, and recording the reversal history of Earth's magnetic field over millions of years, that gave the answer. The continents do not plough through the ocean. The whole seafloor moves. New crust is born at ridges, old crust is consumed at trenches, and the plates are carried along on the conveyor belt in between. The Southeast Indian Ridge, where the doublet happened yesterday, is one segment of that global system. It is a mature, well-studied ridge, active for tens of millions of years. The plates on either side of it are moving apart at what geophysicists call an intermediate rate, about 65 to 75 millimeters a year, 6.5 to 7.5 centimeters, about 3 inches, per year. That sounds slow, and on a human timescale it is. But geological time is not human time. A spreading rate of 70 millimeters a year, sustained over 30 million years, adds up to 2,100 kilometers of new ocean crust. 2,100 kilometers, the width of an entire ocean basin. That is what the seafloor between Australia and Antarctica has been building since the Oligocene. The fact that you cannot see it happen in real time does not mean it is not happening. It is happening right now. Underneath the Southern Ocean, the plates are moving, the new crust is forming, the system is running. There is one more thing to know about how ridges work, and it is the thing that matters most for understanding yesterday's earthquake. Ridges are not straight lines, they are not continuous, they are broken up, segment by segment, by features called transform faults. A transform fault is a horizontal slip fault that connects two segments of a ridge offset from each other, so you have a section of ridge running roughly east-west, then a transform fault running roughly north-south, then another section of ridge running roughly east-west, but shifted some distance south of the first section, then another transform fault, and so on. The segments of the ridge are where new crust is created. The transform faults are where the two plates slide past each other in a strike-slip motion to accommodate the offset. The Southeast Indian Ridge is offset by at least 9 major transform faults between 88 degrees east and 118 degrees east, with individual offsets ranging from 21 to 135 kilometers. The fault zones are long, persistent features, and they are where most of the earthquakes on the ridge system happen. The ridge axis itself produces relatively few earthquakes, because the spreading there is slow and accommodated by magma rather than by brittle fracture. The transform faults are where the stress builds up between two pieces of crust trying to move in opposite directions, and where the stress eventually releases in a quake. The doublet yesterday was almost certainly on a transform fault. The location, the depth, the geometry, and the strike-slip mechanism all point in that direction. The seafloor between Australia and Antarctica was not splitting apart vertically yesterday. 2 blocks of seafloor on opposite sides of a transform fault were sliding horizontally past each other, and one of them slid, and then 11 minutes later the next patch over slid, and that was the doublet. That is the mechanism. That is what this kind of earthquake actually is, in this place, on this kind of structure. And that mechanism, more than anything else, is the reason there was no tsunami warning. Because 2 blocks of crust sliding past each other horizontally is a fundamentally different kind of event from a wedge of crust riding up over its neighbour, the way it does in a subduction zone, and the kind of motion you get on the seafloor is what determines whether the water above is going to move with it or not. Part 4. The difference between splitting and crashing. There is one fact about earthquakes that almost everyone gets wrong, and it is the fact that has the biggest single influence on whether a tsunami forms. The fact is that earthquakes are not all the same. Different earthquakes move the ground in different directions, and it is the direction of the ground motion that determines whether the water above will pile up and run. A subduction zone earthquake, like the kind that hit Japan in 2011 or Sumatra in 2004, happens when one tectonic plate is being forced underneath another. The plate that is going under, the descending slab, gets stuck against the plate riding over it. The stress builds for decades or centuries. When the stuck zone finally breaks, the upper plate snaps upward. The seafloor lurches violently up by meters across an area that can be hundreds of kilometers long. The water column above that area lurches with it. The result is a tsunami, a long wavelength wave that propagates across the ocean at hundreds of kilometers per hour, carries enormous energy, and only becomes visible as a wave when it hits shallow coastal water and piles up. The signature property of a tsunami-generating earthquake is vertical seafloor displacement. A strike-slip earthquake, like the kind that hits the San Andreas Fault in California or the Anatolian Fault in Turkey, happens when two blocks of crust slide past each other horizontally. There is little or no vertical motion of the seafloor or the ground surface. The crust on one side moves north, the crust on the other side moves south, and the boundary between them is the fault. When a strike-slip rupture happens at sea, the seafloor moves sideways. The water column above it does not lurch upward because nothing under it lurched upward. There is no large tsunami because there is no vertical displacement to push the water column up. This is why no tsunami warning was issued for yesterday's doublet, despite both events being magnitude 6 and despite their combined energy being equivalent to a single magnitude 6.2 event. This is not because anyone is hiding anything. This is not because the warning system failed. This is not because the data was suppressed. It is because the warning system looks at the focal mechanism of every earthquake and decides whether the kind of motion that just happened is the kind that displaces water vertically. Strike-slip events on transform faults do not displace water vertically. They displace it sideways, which the ocean handles by simply flowing around the displacement. No wave, no warning. The Pacific Tsunami Warning Center in Hawaii, the National Tsunami Warning Center in Alaska, and the various regional centers that monitor tsunami threats all use the same physics. They look at magnitude, depth, focal mechanism, and location relative to coastlines, and they evaluate whether a wave will form. They issue warnings when the answer is yes. They do not issue warnings when the answer is no. The system is mechanical. The same system would have issued a warning for a similar magnitude thrust earthquake on a subduction zone, and it did not issue one yesterday because the doublet was on a transform fault. There is a corollary to this that matters for the broader story of the doublet. The seafloor between Australia and Antarctica is being pulled apart. The two plates are diverging. New crust is being created at the ridge axis. None of this motion involves one block riding up over another. The vertical motions involved in spreading and in transform fault rupture are tiny compared to the horizontal motions, which means this entire plate boundary, from the Western Indian Ocean to the Macquarie Triple Junction, is essentially incapable of producing a large tsunami. The earthquakes that happen here can be substantial in magnitude, as we'll see in a later part of this story when we talk about the Macquarie Ridge earthquakes of 1989 and 2004, but they do not generate the kind of vertical seafloor disturbance that makes oceans rise. If you wanted a place on Earth to have two magnitude 6 earthquakes happen 11 minutes apart without any threat of damage, you could not have picked a better one than the location of yesterday's doublet. Remote enough that no human population is exposed, a transform fault mechanism that does not generate tsunamis, a spreading ridge setting that does not produce megathrust earthquakes capable of magnitude 8 or 9. The geology of the place essentially guarantees that this kind of event releases its energy without causing damage, which is one of the reasons why most ridge transform earthquakes never make the news, even though they are happening constantly under every ocean on the planet. But the fact that yesterday's doublet was not threatening does not mean it was not unusual. The mechanism explains why it was safe. The mechanism does not explain why it happened twice. Two ruptures, 11 minutes apart, at the same magnitude, on the same fault, at the same location. That coincidence still needs an explanation. Part 5. What a doublet actually is. The word doublet has a specific meaning in seismology. It is not just any two earthquakes that happen close together. It is a pair of earthquakes of comparable magnitude that occur within a short time interval at essentially the same location. The defining feature is the comparable magnitude. Two events of similar size, not a big one followed by a small one, not a foreshock and a main shock, not a main shock and an aftershock, two events that are, for all practical purposes, the same size. This matters because the global earthquake catalogue is full of pairs of events that happen close together in time and space, and almost all of them are explained by the standard pattern of main shock and aftershocks. Barth's law, as we mentioned earlier, says that the largest aftershock is typically about 1 magnitude unit smaller than the main shock. If a magnitude 7 hits, the largest aftershock is usually around 6. The pair you see in the catalogue is a 7 and a 6, and you recognise it as main shock and aftershock. If a magnitude 6 hits, the largest aftershock is usually around 5. The pair you see is a 6 and a 5, and again you recognise the pattern. What you almost never see is two events of the same magnitude, a 6 and a 6, a 7 and a 7. The Barth's law pattern is so consistent across the global catalogue that pairs of equal magnitude events stand out. They are noticed, they get studied, they have been used in deep Earth seismology for a particular reason. If you have two earthquakes that happened at the same location, the seismic waves they produce will travel along nearly identical paths through the Earth's interior, on their way to a given recording station. If you can compare the waveforms from the two events very precisely, you can detect tiny differences in how the waves behaved, which means you can detect tiny changes in the structure of the Earth's interior between the two events. Seismologists studying the rotation of Earth's inner core use doublets exactly for this purpose. The doublets give them identical ray paths, which lets them measure the rotation of the core over the years separating the two events. Without doublets, that measurement would not be possible, so doublets are not just curiosities, they are tools. They are also individually statistically unusual enough that when one happens it is worth paying attention to, because the conditions that produce a doublet are different from the conditions that produce a typical aftershock sequence. What conditions produce a doublet? The most common scenario is that two adjacent fault patches, both of which were close to failure, both ruptured in close succession. The first rupture transferred stress to the second patch and pushed it over the threshold. This is called stress transfer. There are two main flavors of stress transfer. The first is dynamic triggering. When an earthquake happens, it sends out seismic waves. Those waves carry energy. As they pass through neighbouring crust, they impose small, brief stresses on whatever faults they encounter. If a neighbouring fault is already close to failure, the passing wave can push it over the edge. Dynamic triggering operates on timescales of seconds to minutes after the first event, because the waves travel fast and decay quickly. The second flavour is static triggering. When an earthquake happens, it permanently changes the stress field in the surrounding crust. The pattern of stress redistribution depends on the geometry of the rupture, but in general, faults that were oriented favourably will see their stress increase, and faults that were oriented unfavourably will see their stress decrease. Static triggering operates on timescales of hours to years after the first event, because the stress change is permanent, and it takes time for the affected faults to evolve to failure under the new conditions. The 11-minute gap between the two events yesterday is interesting because it sits in the overlap zone between these two regimes. It is too long for pure dynamic triggering. The waves from the first event would have arrived at the second patch within seconds, and any dynamic effect should have produced a rupture immediately. It is also short for static triggering. Most static triggering studies focus on events hours to days apart, not minutes. So either there was a delayed dynamic effect, where the second patch was very close to failure, and the slow process of stress accumulation that brought it to that state was tipped over by the first event, or there was a faster static effect than is usually modelled. Or more likely, both processes contributed. The other thing that the doublet tells us is something about the geometry of the local fault system. The fact that two events of identical magnitude happened at the same location strongly suggests that the local section of the transform fault is segmented into approximately equal-sized blocks. Each block has roughly the same area of fault surface. Each block stores roughly the same amount of strain. Each block releases roughly the same amount of seismic energy when it ruptures. This is consistent with the modern understanding of mid-ocean ridge transform faults, which are not single continuous structures, but rather chains of smaller fault segments separated by smaller obstacles, stepovers, and bends. The segmentation explains why ridge transform earthquakes tend to cluster in characteristic magnitudes for any given fault, why magnitude 6 is a common size on a fault like this, and why two ruptures of similar size on adjacent segments is not an unreasonable thing to expect over decadal timescales. The unusual thing yesterday was the timing. Two segments rupturing within 11 minutes of each other is the kind of clustering that does not happen often. Globally, doublets at this scale are documented but rare. On the Southeast Indian Ridge specifically, there is no recent documented W6.0, mu6.0 pair at the same coordinates with this kind of separation. Today's event is unusual on this stretch of ridge. The combination of unusual timing, equal magnitudes, identical locations, and an interpretable physical mechanism makes this a real scientific event. Not a glitch, not a duplicate database entry, not a coincidence so weird it requires reaching for an exotic explanation. A real, documented, rare, but explainable case of paired stress release on an oceanic transform fault system, captured cleanly by the global seismic network. It is worth slowing down for a moment on the catalogue work itself, because the catalogue is what we have. Every modern earthquake report you have ever seen, the magnitudes, the depths, the times, the coordinates, is the output of an automated processing pipeline that takes raw waveforms from hundreds of seismograph stations and reconstructs the source. The processing starts with the detection of seismic phases at individual stations. A station in Tasmania records a vertical ground motion. The detection algorithm flags the onset of that motion and labels it as a P wave, the first arriving compressional phase, travelling from the source to the station through the interior of the Earth. Other stations record their own onsets. The system collects the arrival times from all the stations and uses them to triangulate the location of the source, the origin time of the event, and the depth. From the amplitudes of the waves at each station, corrected for distance and for the radiation pattern of the source, the system estimates the magnitude. All of this happens automatically within minutes for every earthquake above the catalogue's detection threshold. For the doublet, this process happened twice. 2 independent triangulations, 2 independent origin times, 2 independent magnitudes. Both events were detected by enough stations that the solutions are well constrained. The locations of the 2 events agree at the level of a kilometre. The magnitudes agree at the level of 0.1. The depths agree at the default of 10 kilometres. This is exactly what you would expect for 2 real, separate earthquakes that happened in nearly the same place at nearly the same time. If the system were just duplicating a single earthquake, the 2 reported origin times would be artificially aligned, and the magnitudes would be unrealistically identical. The processing system is sophisticated enough that it has had to handle such cases in the past, and the algorithms have filters that catch obvious duplications. The doublet passed those filters because it was 2 real events, not one event being reported twice. The European Mediterranean Seismological Centre, which maintains its own independent catalogue, drawing from a different mix of stations and processing techniques, confirms the doublet. The EMSC location, the EMSC origin times, the EMSC magnitudes all match the USGS values within their respective uncertainties. The 2 agencies do not coordinate their processing, and the fact that both arrived at the same conclusion is the strongest evidence that the doublet is real. Other regional networks that pick up signals from this part of the world, including the Australian Seismological Network and the New Zealand GeoNet system, also recorded both events. There is no agency that has reported only one event. The doublet appears in every catalogue that covers this region. The next step in the cataloguing process is what is called the moment tensor inversion. Beyond just locating the source and estimating the magnitude, the moment tensor inversion reconstructs the geometry of the rupture. It tells you whether the motion was strike slip, thrust, or normal. It tells you the orientation of the fault plane and the direction of slip. For events of magnitude 6 in well-recorded regions, the moment tensor solution is usually published within a day or 2 of the event by the Global Centroid Moment Tensor Catalogue and other groups. As of the source document cut-off time, the moment tensor solutions for the doublet had not yet been formally published, but the location of the events on a known transform fault structure, combined with the absence of significant vertical seafloor displacement, implied by the lack of a tsunami, strongly indicates that both events were strike-slip ruptures on a transform fault. When the moment tensor solutions become available, they will most likely confirm this interpretation. This is the level of detail at which modern seismology operates. 2 events at the edge of Antarctica, recorded by instruments 1,000 kilometers away, processed by independent agencies on opposite sides of the world, cross-checked against each other, and reported in catalogues that anyone can access. The level of confidence we can have in the basic facts of the doublet is high. The level of detail we have on the geometry of the rupture is somewhat lower, because the closest stations are far away, and the moment tensor inversion at these distances has larger uncertainty. But the core facts are solid. 2 events, same magnitude, same location, 11 minutes apart. The catalogue says so, and the catalogue is right. Part 6. Why two patches broke at once. The physical question underneath the doublet is, what brought two adjacent fault patches to the point of failure at almost the same time? The answer, as best as we can reconstruct it from 1,000 kilometers away, involves a slow build-up of stress on a transform fault that had been accumulating strain for some time, followed by a rupture that not only released its own stress, but also triggered a neighbouring patch that was also close to failure. The slow part of the story is the spreading itself. The Australian plate and the Antarctic plate have been moving apart at the latitude of the doublet for tens of millions of years. The motion is steady at about 70 millimeters a year, and the deformation that motion produces is taken up along the entire plate boundary. Most of the spreading happens at the ridge axis through magma intrusion and the creation of new crust. Some of the deformation happens on the transform faults that offset the ridge segments. The transform faults are the brittle, frictional structures that accommodate the geometric offset between the spreading segments. They store strain, they release it as earthquakes, and they do this on a slow, persistent cycle that has been running for as long as the ridge has been active. The patches of the transform fault yesterday had been storing strain for some interval of time before they ruptured. We do not know exactly how long, because we do not have direct observations of the local strain accumulation over historical time, but we can estimate. A magnitude 6 event releases roughly 10 to the 18th Newton meters of seismic moment. That moment is the integral of the stress drop over the rupture area, and on a transform fault with stress drops of a few megapascals, that corresponds to a rupture area of a few hundred square kilometers. To accumulate enough strain to feed that rupture, at a strain rate consistent with the 70 mm per year spreading and the local geometry, you need somewhere on the order of decades to a century, depending on how efficiently the fault is loaded. So picture the situation just before yesterday's first earthquake. There is a transform fault between two ridge segments. The fault is segmented into approximately equal-sized blocks, each of which can fail in a magnitude 6 rupture. One of those blocks has been storing strain for about 100 years. The block right next to it has also been storing strain for about 100 years, because the loading on both blocks is roughly the same. Both blocks are close to failure. Each block has a slightly different precise stress state, depending on the local frictional conditions, the temperature, the presence or absence of small amounts of fluid in the crust, and the particular history of how the surrounding stress field has evolved. Whichever block happens to be closest to its individual failure threshold goes first. At 51 minutes past 2 o'clock yesterday, that block went. The rupture initiated somewhere on the fault, propagated outward at a few kilometers per second, and unzipped the entire patch in a few seconds. The seismic energy released came out as the waves that the global seismic network recorded a few minutes later. The local stress field changed. The block that had been pulling the adjacent block toward failure was now relaxed. The adjacent block found itself, in the aftermath of the first rupture, with a different stress state than it had before. Some directions of stress had increased, some had decreased. The Coulomb stress on the favourably oriented part of the adjacent fault had gone up by some small amount. In most cases, that small change is not enough to trigger an immediate rupture. The adjacent block keeps storing strain and eventually fails on its own timescale, months or years later. But in some cases, the small change is enough. If the adjacent block was already extremely close to its failure threshold, the additional push from the static stress change in the surrounding field, possibly combined with whatever residual dynamic shaking was lingering as the seismic waves continued to ring through the crust, is enough to push it over the edge. The adjacent block ruptures in its own magnitude 6 event. And because the two blocks are similar in size and were similar in their pre-rupture stress states, the second rupture releases nearly the same amount of energy as the first. 11 minutes later, the second event was logged. Same magnitude, same coordinates within the catalogue's spatial resolution, same depth. The doublet was complete. This story is, in its outline, well understood seismology. Stress transfer between adjacent fault patches is one of the most studied phenomena in earthquake physics. The mathematics of how a rupture changes the surrounding stress field has been worked out in detail. The empirical record of doublets and triplets and multiplet events at various scales has been built up over decades. The mechanism we have just described is not exotic. It is the standard explanation for paired earthquakes of this kind. What is unusual about yesterday is not the mechanism but the timing. 11 minutes is a short interval, even for stress transfer events. Most stress transfer pairs are separated by hours to weeks. Pairs separated by minutes are documented but rare, and they imply that the second patch was very close to failure indeed, possibly within a few % of its threshold, and that the first rupture's static effect was just enough to push it the rest of the way. The 11-minute gap is, in this reading, a measure of how tightly the local fault system was loaded. Both patches were ready to go. The first one just happened to go first by about 10 minutes, and then it took the second one with it. The other thing this tells us is something about the future seismic behaviour of this stretch of ridge. The two patches that ruptured yesterday have now released their accumulated strain. They will not produce another magnitude 6 on the same patches for decades, at minimum. The fault is now in a relaxed state on those segments. There may be smaller adjustments. There may be even smaller events as the system settles. But the next significant earthquake on this stretch of ridge will probably come from a different patch, one that was not part of yesterday's doublet, and it will probably not happen for some years to come. The doublet is, in this sense, a discharge event. The local stress has been released. The ridge is quieter now than it was yesterday morning. There is a useful way to think about transform fault behaviour that comes from comparing oceanic transforms to their continental cousins, the strike-slip faults on land that everyone has heard of. The San Andreas Fault in California is a continental transform fault, and it has been studied in extraordinary detail because it runs through major population centres and produces earthquakes that affect millions of people. The Anatolian Fault in Turkey, the Alpine Fault in New Zealand, the Dead Sea Transform in the Middle East are all continental transform faults of similar type. They produce earthquakes of similar mechanism to oceanic transform fault events. Strike-slip ruptures where two blocks slide horizontally past each other. The same basic physics applies, but there is a difference between the continental versions and the oceanic versions, and the difference comes from the temperature structure of the crust. Continental crust is granitic, relatively cold, and brittle to depths of 15 to 20 kilometers. The brittle ductile transition, where the rock starts behaving plastically rather than rupturing in earthquakes, sits at around 15 to 20 kilometers depth under continents. Oceanic crust is basaltic, hotter for its depth, and brittle only to about 7 to 10 kilometers. The brittle ductile transition under an oceanic transform is shallower. This means that earthquakes on oceanic transforms are confined to a thinner brittle layer, which limits how large a single rupture can be. You can get a magnitude 6 earthquake on an oceanic transform pretty easily. You can get a magnitude 7 on a long stretch of oceanic transform if the geometry allows. Magnitude 8 is harder, and it is generally only achieved on the longer, more complex transform systems like the Macquarie Ridge, where some compression has been added to the strike-slip motion. You almost never see magnitude 9 on a pure oceanic transform, because there is simply not enough brittle fault surface to accumulate that much strain in a single segment. The doublet yesterday was within the typical magnitude range for an oceanic transform fault rupture. A magnitude 6 is a standard size for this kind of event. What was unusual was not the magnitude. What was unusual was the timing. Two events of standard size in a non-standard pattern. The combination is what makes this worth a closer look. If you saw a single magnitude 6 event in this location, you would log it and move on. The doublet pattern is what made the system stop and look. There is also a question of how representative the doublet is of the underlying seismic process. For any given fault, the long-term earthquake catalogue gives you a statistical picture of how often events of various magnitudes happen. The relationship between the number of events and their magnitude follows a power law called the Gutenberg-Richter relation, where the logarithm of the number of events of a given magnitude or greater is a linear function of magnitude with a slope of approximately -1. This means that for every magnitude 6 event on a given fault, you expect roughly 10 magnitude 5 events, 100 magnitude 4 events, and so on. The Gutenberg-Richter relation is one of the most universal empirical results in seismology, and it holds across an enormous range of tectonic settings. For an oceanic transform fault like the one that produced the doublet, the local Gutenberg-Richter rate sets the expectation for how often you should see events of each magnitude. The Southeast Indian Ridge as a whole produces events in the magnitude 5 range frequently, magnitude 6 events every few months on average across the entire ridge system, and magnitude 7 or larger events only rarely. A doublet of 2 magnitude 6 events on adjacent patches, on the same day, 11 minutes apart, is not impossible under the Gutenberg-Richter framework, but it is statistically uncommon. The probability of two independent magnitude 6 events happening within 11 minutes of each other anywhere on the Southeast Indian Ridge can be calculated from the average rate, and it works out to something on the order of once every several decades to once per century. The probability of two independent magnitude 6 events happening at the same location within 11 minutes is much smaller, which is why, when this kind of thing does happen, the most likely explanation is not independence. The most likely explanation is that the two events are dynamically or statically coupled, which brings you back to the stress transfer picture we have already described. But none of this is what the viral posts have been saying about the doublet. The viral posts have not been talking about transform fault stress transfer, or Coulomb stress changes or fault segmentation. The viral posts have been talking about something else entirely. They have been talking about the Earth itself, and what they think the earthquakes mean. And that brings us to the secondary story underneath this event, the one that turns out to be at least as interesting as the doublet itself. Part 7. The viral theory going around. In the hours after the doublet was catalogued, a particular framing started circulating on social media. The framing claims, in short, that earthquakes like yesterday's are evidence that the Earth is expanding, that the planet is slowly growing in radius, that if you compressed the modern Earth down to a smaller diameter, all of its land masses would fit together to enclose the surface without any oceans, that Pangaea, as we currently understand it, never existed in the form most textbooks describe, that Earth used to be smaller, that it is getting bigger, and that hundreds of millions of years from now, it will be the size of Jupiter or Saturn and will have transformed into a gas giant. This is the expanding Earth hypothesis. It is not new. Versions of it have been around for nearly a century. It has a documented intellectual history and named proponents, and it deserves to be engaged with seriously, both because the intuitions that produce it are not crazy, and because dismissing it without explanation is exactly the kind of move that makes it more credible to viewers who are encountering it for the first time. So let us engage it seriously. There are 3 observations that make expanding Earth feel intuitive at first glance. The first observation is that mid-ocean ridges really are spreading. New ocean crust really is being created at the ridges. The seafloor really is getting wider over time. This is not in dispute. It is one of the most rock-solid observations in modern Earth science. Anyone can look at the maps of seafloor age, see the symmetric magnetic stripes on either side of every ridge axis, and recognize that the ocean basins are growing. The Atlantic Ocean is wider today than it was 100 million years ago. The Pacific Ocean has its own complicated history. The Indian Ocean opened up over the last 150 million years as India broke away from Africa and Antarctica. All of this is real, documented, and uncontroversial. The second observation is that if you take a globe of the modern Earth and shrink it down to about 60% of its current diameter, the continents on it really do appear to fit together more cleanly than they do on the full-sized globe. The continental shelves of Africa and South America come together. The shapes of Australia, Antarctica, India and Madagascar can be assembled to cover almost the entire smaller globe with no leftover ocean space. Physical models showing this have been built since the 1930s, and seeing one is a striking visual experience. The continents do look like they fit. The visual coincidence is real. The third observation is that if you accept that the Earth used to be smaller, you no longer need the vast Panthalassa Ocean that the standard Pangaea reconstruction puts on the other side of the supercontinent. The standard reconstruction shows Pangaea as a single landmass with a single ocean surrounding it, a single ocean that covered more than half of the planet's surface. Critics of the standard model have asked, why was there such a vast empty ocean? Why is the geometry of Pangaea plus Panthalassa so asymmetric? On a smaller Earth, this question goes away. The continents fill the whole sphere. There is no Panthalassa. The visual elegance of the model is, again, real. Add up these 3 things and you get an explanation that feels parsimonious. The Earth is growing. Ridges produce new crust. Subduction does not destroy crust at the same rate. The surface area is increasing. The continents that fit together on a smaller globe were once joined together on a smaller globe. The Pangaea Ocean is a myth, an artifact of trying to fit modern continental positions onto a planet whose size you have not adjusted. Today's doublet on the Southeast Indian Ridge is one more piece of evidence. The seafloor is splitting open. The Earth is growing. You have been told the wrong story. This is the framing that is circulating, and the reason it gets traction is that the 3 observations that underlie it are not wrong. They are real observations. Anyone can verify them. The continents really do fit on a smaller globe. The seafloor really is spreading. The geometry of Pangaea really does have an asymmetry problem on a full-size planet. The hypothesis is taking real evidence and assembling it into a narrative. The problem with the narrative is not the evidence it cites. The problem is the evidence it does not cite. The problem is what else has been measured about the Earth, by people working on this for the last 70 years, that the expanding Earth framing has to either ignore or explain away. And when you put the full set of measurements on the table, the framing breaks. Not because of one decisive disproof, but because of 6 independent lines of evidence, each of which is sufficient on its own to falsify the hypothesis, and which together leave no room for it to survive as a serious scientific claim. To get to those 6 lines of evidence, though, we need to back up and talk about where this hypothesis came from in the first place. Because it has a real history. It was not invented on social media. It was developed by serious people in the middle of the 20th century, working with the best data they had at the time, and it took several decades for the measurements that refuted it to become available. The history matters because it tells you both why smart people once believed this, and why we now have more information than they did. Today's doublet is being attached to a theory that was already obsolete in the 1970s, but the people circulating it on social media generally do not know that, and the honest scientific response is to walk through how we got to where we are. Part 8. Hilgenberg and Carey. The earliest documented model maker of the expanding Earth idea was a German engineer and amateur scientist named Ott Christoph Hilgenberg. In 1933, Hilgenberg published a book called Vom wachsenden Erdball, which translates roughly as About the Growing Earth. The book presented papier-mâché globes that Hilgenberg had constructed by hand. He took the modern coastlines of the continents, fit them together as cleanly as he could, and discovered that they would close up to enclose a sphere about 60% of the diameter of the modern Earth, with no leftover ocean space. The physical demonstration was striking. Anyone who saw one of Hilgenberg's globes had to admit that the continental fit on a smaller Earth was visually compelling. What Hilgenberg did with that demonstration was to argue that the Earth had been growing over geological time. He proposed that the mass and volume of the planet had increased since the Mesozoic, that the present-day continental positions reflected the trace of where the continents had ended up after expanding away from their original positions on a smaller Earth, and that the modern oceans were the spaces opened up by that expansion. To explain how the Earth could grow, Hilgenberg invoked a mechanism he called the absorption and transformation of ether energy into normal matter. Ether was, in 1933, still occasionally discussed in fringe physics circles as a hypothetical medium pervading space. The mechanism Hilgenberg proposed was that this ether could be converted somehow into ordinary matter inside the Earth, gradually adding mass and volume over time. The ether mechanism was not a respectable physical idea, even in 1933. By the early 1900s, the famous Michelson-Morley experiment of 1887 had already eliminated the luminiferous ether as a real physical medium, and Einstein's special relativity in 1905 had given a complete theoretical framework that made the ether unnecessary. By the 1930s, ether had been retired as a serious scientific concept for over 30 years. Hilgenberg was working outside the mainstream, and his ideas were largely ignored by the geological community of the time. There was also a practical problem with Hilgenberg's reconstructions. The visual fit of continents on a smaller globe was compelling, but not actually rigorous. Hilgenberg was working by eye. He was bending continental outlines slightly here and there to make them close up. He was not accounting for the rotation of any continental fragment over the time he proposed for the expansion. Modern continental drift reconstructions, even at the time, were already using more sophisticated methods to put continental positions through time. The Hilgenberg approach was a striking demonstration, but not a quantitative scientific argument, and the geological mainstream of the 1930s recognized that. The next major figure in the expanding Earth story was Samuel Warren Carey. Carey was an Australian geologist born in 1911 who became the founding professor of geology at the University of Tasmania in 1946. He was an early and enthusiastic advocate of continental drift in the 1940s and 1950s, at a time when continental drift was still controversial in the global geological community. Wegener's hypothesis had been around since 1912, but had not been generally accepted, and the work of confirming or refuting it was ongoing. Carey was part of the group of geologists, mostly in the southern hemisphere, who had been looking at the fit of the southern continents and accumulating evidence that continental drift was real. He was a serious scientist with a serious institutional position. In 1956, Carey hosted a major symposium at the University of Tasmania on what was then called the continental drift hypothesis. The symposium brought together leading researchers, and the proceedings were published as a book in 1958. During and after the symposium, Carey developed his own version of the expanding Earth hypothesis, independently of Hilgenberg's earlier work. He only learned of Hilgenberg's papier-mâché globes after his own ideas had taken shape. Carey was working from a different starting point. He had access to the new data on seafloor topography and the patterns of earthquake distribution that had been emerging in the 1950s, including the discovery of the global mid-ocean ridge system. He noticed, as everyone working on plate tectonics was noticing, that the seafloor was spreading at the ridges, and he made an argument that, in 1956, was actually reasonable to make. Carey's argument was that the rate at which new crust was being created at the ridges, which had become measurable in a rough way by the late 1950s, was not balanced by any equivalent rate of crust destruction. Subduction zones had been identified by then. The deep trenches around the Pacific Rim were known, but the rate at which crust was being consumed at subduction zones was not yet directly measured. Carey looked at the available data and concluded that the spreading was faster than the subduction, and that therefore the total surface area of the Earth had to be increasing. The continents were drifting because they were being carried along on an expanding planet. In 1976, Carey published a book called The Expanding Earth, which laid out his hypothesis in detail. The book presented his arguments for an expanding planet, his reconstructions of continental positions on smaller paleo-Earths going back through geological time, and his interpretation of the geological record as supporting his hypothesis. The book was widely read in geological circles, and it kept the expanding Earth idea alive as a serious, if minority, position through the 1970s and into the 1980s. Carey was a real scientist working on a real problem. His objection to the conventional picture, that subduction could not balance spreading, was a reasonable objection given the data available in 1956. It is the kind of objection that scientific progress is built on. Someone notices a potential inconsistency in the standard model, raises it, and forces the community to either explain it away or revise the model. That is how science works. Carey did his job. The problem for the expanding Earth hypothesis was that the data Carey was missing started arriving in large quantities through the 1960s, 70s, 80s, and beyond. Direct measurements of plate motion, both from paleomagnetism and later from GPS, made it possible to measure spreading rates and subduction rates separately and to compare them. The subduction rate measurements showed, very quickly, that subduction was consuming crust at very nearly the same rate that spreading was creating it. Carey's original objection turned out to be based on an underestimate of how fast subduction was actually happening, an underestimate that was unavoidable in 1956 because the right measurements had not yet been made. By the time Carey's book was published in 1976, the data was already starting to show that the global crustal budget was approximately balanced. By the 1980s and 1990s, the balance had been confirmed at high precision by independent measurements. Carey's original argument no longer held, but the hypothesis had developed a momentum of its own, and it survived in the science fringe long after the data had moved on. That is the history. The expanding Earth hypothesis was a reasonable speculation in 1956. It was a serious, if minority, scientific position through the 1970s. It has been refuted in detail since the 1980s by direct measurement, and the version that has been circulating on social media this week with today's doublet attached to it as evidence is essentially the Carey hypothesis stripped of its scientific caveats, presented as if the refutation never happened. The viral framing knows about the spreading and knows about the smaller globe continental fit, and does not know about the 70 years of subsequent geophysical measurement that have closed the case. That is what the next part of this video is about. The 6 lines of evidence that have refuted the hypothesis, walk through one at a time, each connecting back to today's doublet. Part 9. 6 ways the theory falls apart. The expanding Earth hypothesis is not refuted by a single decisive experiment. It is refuted by 6 independent lines of evidence, each of which, on its own, is sufficient to falsify it. Together they leave no room for the hypothesis to survive as a serious scientific position. Walk through them slowly. Each one connects back to today's doublet at the end. The first line of evidence is direct measurement of Earth's radius. In 2011, a research team led by Xiaoping Wu of NASA's Jet Propulsion Laboratory, with collaborators at institutions in France and the Netherlands, published a measurement of the rate of change of Earth's average radius. The team combined 4 independent techniques: satellite laser ranging, which uses lasers to measure precise distances between ground stations and reflectors in orbit; very long baseline interferometry, which uses arrays of radio telescopes to measure the position of distant quasars, and from that to measure the relative positions of the radio telescopes themselves; the global positioning system, which gives precise displacements of ground stations over years and decades; and gravity measurements from the GRACE satellites, the Gravity Recovery and Climate Experiment, which mapped Earth's gravitational field in unprecedented detail. All 4 of these techniques have different systematic errors, different biases, different ways of being wrong. Combining them lets you cancel out the individual errors and get a measurement that is robust to the kinds of mistakes any single technique might make. The result that the team reported was that Earth's average radius is changing by approximately 0.1 mm per year, about 1/10 of a millimeter, about the thickness of a human hair, as one of the press releases noted at the time. This is a measurement with a stated uncertainty, and the uncertainty is large enough that the actual rate of radius change is statistically indistinguishable from 0. Within current measurement precision, Earth is not getting larger. It is not getting smaller. It is the same size today as it was when the measurement started. Compare that to what expanding Earth would require. For Earth to have grown from 60% of its current diameter to its current diameter over the timescale Carey proposed, somewhere between the Mesozoic and the present, around 250 million years, the radius would have had to increase by about 2,500 kilometers, or about 10 millimeters per year on average. That is 100 times faster than the measurement uncertainty in the 2011 study. If Earth were growing at the rate Carey proposed, the measurement would have detected it at very high confidence. It did not. The measurement is consistent with 0 growth. The expanding Earth hypothesis, as a quantitative claim about Earth size, is directly falsified by this single line of evidence. The second line of evidence is the observation of subduction in action. Carey's original objection in 1956 was that subduction could not balance spreading. That objection has been tested directly, repeatedly, over the past 7 decades. The subduction zones around the Pacific Rim are some of the most heavily instrumented regions on Earth. The convergence rates at the Aleutian Trench, the Japan Trench, the Mariana Trench, the Tonga-Kermadec Trench, the Peru-Chile Trench have all been measured by GPS, by paleomagnetic analysis of the seafloor age stripes, and by direct tracking of plate motions over time. The Pacific Plate is being consumed beneath the Aleutians at about 6 centimeters per year, beneath Japan at about 8 centimeters per year, beneath Tonga-Kermadec at about 8 to 9 centimeters per year. The Nazca Plate is being consumed under South America at 6 to 10 centimeters per year. The total subduction rate globally is now well constrained, and when you add it all up, it matches the total spreading rate at the world's mid-ocean ridges within measurement uncertainty. Crust is being created at the ridges. Crust is being destroyed at the trenches. The net change in surface area is 0. This is exactly the balance that Carey said could not exist. The measurements show that it does exist, and that it has existed throughout the period for which we have data. The third line of evidence is paleomagnetism. When magma cools to form igneous rock, the iron-bearing minerals in the rock orient themselves along the prevailing magnetic field direction at the time of cooling. Once the rock solidifies, the orientation is locked in. If you measure the magnetization of ancient rocks, you can recover information about Earth's magnetic field at the time those rocks formed, including the position the rocks were at relative to the magnetic poles. Paleomagnetic measurements have been made on rocks of all ages from all over the world, and the results constrain the geometry of Earth's surface throughout geological time. If Earth had been substantially smaller in the past, the geometry of the magnetic field, the relative positions of paleomagnetic poles measured from different continents at the same age, and the distances implied between those continents, would all show systematic distortions reflecting the smaller planet. They do not. The paleomagnetic record is consistent with an Earth of roughly its current radius throughout the past several 100 million years. Within the uncertainty of the measurements, no expansion is required. The fourth line of evidence is the energy budget. For Earth to gain mass at the rate expanding Earth requires, the planet would need to be adding matter from somewhere. The ether mechanism Hilgenberg proposed is not a real physical phenomenon. The viral version of expanding Earth that circulates today does not generally specify a mechanism at all. But whatever mechanism you propose, it has to be capable of adding mass at the required rate, and the required rate is enormous. To grow from 60% of modern diameter to modern diameter over 250 million years, Earth would need to add about 1,000 quintillion kilograms of mass, distributed over that time, or roughly 300 million tons per second on average. That is a continuous addition of 300 million tons of new matter every second of every day for 250 million years. The actual measured rate of meteoritic accretion onto Earth, which is the only known source of new matter from outside the planet, is about 40,000 tons per year, total from all sources combined. That is roughly 15 orders of magnitude too small to support the proposed expansion. There is no other observed source of new matter. There is no measured energy flux that could be converting energy into mass at the required rate. The energy budget impossibility is not a minor objection. It is a 13-digit shortfall between the rate expanding Earth needs and the rate we can actually measure. The fifth line of evidence is rotational dynamics. Earth's moment of inertia depends on its mass distribution and radius. If the planet were growing, its moment of inertia would be increasing, and its rotation rate would be slowing in response. The conservation of angular momentum, which is one of the most fundamental principles in physics, would require it. Earth's rotation rate is in fact slowing, very slowly, by about 1.5 milliseconds per century. This slowing has been measured for over a century, and it is well understood. It is caused entirely by tidal friction between Earth and the Moon. The Moon races tides in Earth's oceans, and the friction of the tidal bulge moving across the planet transfers angular momentum from Earth to the Moon, slowing Earth's rotation and pushing the Moon further away from us. The observed rate of rotational slowing is consistent with the measured strength of the lunar tidal friction. There is no additional slowing beyond what tides account for. If Earth were growing at the rate Carey proposed, the additional moment of inertia increase would produce an additional rotational slowdown of about 30 milliseconds per century, 20 times faster than the actually measured rate. The measured slowing leaves no room for Earth to be growing. The sixth line of evidence is the continental fit problem itself. The expanding Earth hypothesis is built around the observation that the continents fit together more cleanly on a smaller globe than on the modern Earth. This is true if you look at the visual fit and ignore the geological record. But Alfred Wegener, in 1912, made a different argument from the same starting point. Wegener also noticed that the continents fit together. His explanation was that the continents had once been joined as a single supercontinent and had drifted apart since. He did not propose a changing Earth radius. He proposed continental drift on a fixed-size Earth. And the question of how well the continents fit on his fixed-size Earth has been answered in detail by modern plate tectonic reconstructions. The fit is, in fact, quite good. Africa and South America come together cleanly along their continental shelves. Australia, Antarctica, and India can be assembled into a single eastern Gondwana. The geometric tightness of the Pangaea fit on a normal-sized Earth is excellent. The Pangaea Ocean covers the other side of the planet, because the supercontinent occupied only a fraction of the surface, and that single ocean really did exist. We can see its trace in the geology of the Pacific Basin, which is the descendant of Pangaea. The visual elegance of the smaller globe fit is a coincidence of geometric closure, not evidence of a smaller planet. The Pangaea on modern Earth reconstruction explains the continental fit equally well, without requiring the planet to change size. 6 independent lines of evidence: direct radius measurement that finds no expansion, direct subduction rate measurement that closes the spreading versus consumption budget, paleomagnetic constraint on past geometry, energy budget impossibility for any plausible mass addition mechanism, rotational dynamics that leave no room for additional slowing, and the Wegener-style continental fit on a fixed-size Earth that matches the visual evidence the hypothesis is built on without requiring expansion. Any one of these is enough to falsify the hypothesis. All 6 together close the question. There is a useful exercise in considering what it would take for any of these 6 lines of evidence to be wrong, because the expanding Earth hypothesis as currently circulating implicitly requires that they all be wrong in the same direction for the hypothesis to survive. The satellite geodesy measurement of Earth's radius would have to be systematically biased towards zero by an amount comparable to its measurement uncertainty, and biased in a way that no one has noticed despite the techniques being used for other applications by scientists working in independent labs around the world. The subduction rate measurements would have to be systematically overestimating subduction, again across multiple independent techniques and research groups, in a way that conveniently makes the global crustal budget look balanced when it is not actually balanced. The paleomagnetic record would have to be misinterpreted in a systematic way that makes the past Earth look the same size as the present Earth, when it actually was not. The energy budget calculation would have to be miscalculated by 15 orders of magnitude, which is the kind of error that does not happen by accident. The rotational dynamics analysis would have to be ignoring some compensating effect that exactly cancels the rotational signature of expansion, again with no one noticing, and the Wegener continental fit reconstructions would have to be artificially good in some way that the geological community has not recognized. The probability that all 6 independent lines of evidence are wrong in the same direction, in a coordinated way, is essentially zero. Each line of evidence comes from a different subdiscipline, different measurement techniques, different research groups, different funding agencies, different countries. For the conclusion to be wrong in the way expanding Earth requires, you would need a conspiracy among the world's geophysicists, geodesists, paleomagnetists, satellite engineers, and so on, all collaborating to hide the same kind of finding. That conspiracy would need to have lasted for 7 decades, included thousands of researchers, and not produced a single defector willing to share the supposedly suppressed evidence. The probability of such a conspiracy is, to put it gently, lower than the probability that the hypothesis is simply wrong. The actual situation is much simpler. The 6 lines of evidence are independent, they were developed by independent groups, and they all arrived at the same conclusion because that conclusion is what the data shows. Earth is not expanding, the radius is stable, the crustal budget balances, the continents fit on a fixed size Earth in their reconstructed positions. The visual elegance of the smaller globe model is an artifact of the geometric closure problem, not evidence of a smaller planet. Plate tectonics works. Continental drift on a fixed size Earth works. The case is closed at the level of evidence, even if it is not closed at the level of viral conversation. It is worth saying, plainly, that being wrong about expanding Earth does not make you a bad person. The intuitions that lead to it are honest intuitions. The visual demonstration is striking. The math of the global crustal budget in 1956 was genuinely uncertain. Smart, careful scientists held versions of this hypothesis for legitimate reasons in the middle of the 20th century. What changed is not the smartness of the scientists. What changed is the data. The measurements that closed the case did not exist in 1956. They did exist by the 1980s. They have been refined continuously since. The question of whether the Earth is expanding was an open question for about 30 years. It has been a closed question for about 40 years. The viral framing today is operating on a 30-year-old open question that has been closed for 40 years, and the closure is well documented. None of this is hidden. None of this requires advanced training to understand. It is in the introductory geology textbooks. It is on the NASA website. It is in the open scientific literature. The reason it is not in the viral posts is that the viral posts do not have the format to carry it. Today's doublet on the Southeast Indian Ridge is, according to the viral framing, evidence for expanding Earth. But every one of the 6 lines of falsification applies. The doublet is one snapshot of seafloor spreading at the ridge. Spreading is real. New crust is being created. At the same time, on the other side of the Pacific, the Aleutian Arc is consuming Pacific crust at 6 centimeters a year. Yesterday, the Aleutians had its own cluster of moderate events. A magnitude 5.2 near Adak, a magnitude 5.2 at the Andrianoff Islands, a magnitude 4.6 in the Rat Islands, old crust being destroyed in the trench, new crust being created at the ridge, both happening simultaneously, both visible in the same week of catalogue data. The conservation equation is balancing in real time on both sides of the world. The doublet is not evidence the Earth is growing. The doublet is one half of an equation whose other half is being satisfied at the exact same time by the very subduction zones the expanding Earth hypothesis says cannot keep up. Part 10. Why it still spreads online. The expanding Earth hypothesis is scientifically obsolete. The 6 lines of evidence we just walked through are not contested. They are not on the edges of the scientific community. They are accepted by essentially every working geophysicist on the planet. There is no peer-reviewed literature defending the hypothesis at present. The few researchers who continue to advocate for it work outside the mainstream and have not produced data that the rest of the community has been able to confirm. As a scientific claim, the question is closed. So why does it keep coming back? Why, every few months does a new viral post appear claiming that the Earth is expanding, that Pangaea never existed, that the continents fit on a smaller globe, and that some current event proves it? Why does the question keep getting opened up again, decades after the case has been settled? There are several reasons, and none of them are about the data. The first reason is the visual demonstration. The papier-mâché globes that Hilgenberg built in 1933 are still compelling when you see them. The image of all the modern continents fitting together to cover the entire surface of a smaller Earth is an image you can hold in your mind. It is the kind of image that lodges. Once you have seen it, it does not go away. The full set of 6 counter-arguments against expanding Earth is more abstract. Satellite laser ranging measurements do not produce a memorable visual. Paleomagnetic pole positions do not look like anything when you draw them on a map. Energy budget calculations do not have a picture. The hypothesis has one striking image. The refutation has a list of bullet points. Images win. The second reason is the structure of viral information. Social media rewards clearly stated claims that can fit in a post. The expanding Earth framing fits in a post. The refutation does not. Saying the Earth is expanding into a gas giant is a complete claim in 8 words. Saying the rate of subduction at the global trench system matches the rate of spreading at the global ridge system within measurement uncertainty, which leaves no room for the surface area to grow, is 27 words and requires the reader to know what subduction is and what measurement uncertainty means. The format favours the claim, not the rebuttal. The third reason is the appeal of the "you have been lied to" framing. A theory that explains everything and that the mainstream has rejected feels, to many people, more interesting than the mainstream itself. There is a particular psychological draw to hidden knowledge, to the idea that the experts are wrong and that the truth has been suppressed. Expanding Earth fits that template. The framing implicitly says, your geology teacher was wrong, your textbooks are wrong, the scientific establishment has been lying to you, and here is the real story. That framing creates a feeling of empowerment. It says you are smart enough to see through the deception. It rewards skepticism toward established authority, which is a virtue when it is calibrated correctly, and which is a vulnerability when it is calibrated against well-supported science. The fourth reason is that the hypothesis offers a simple, unified explanation for complicated observations. Plate tectonics, the actual modern theory, is messy. It has subduction zones and spreading ridges and transform faults and slab pull and ridge push and continental collision and rift valleys. It requires you to keep track of a dozen interacting processes. Expanding Earth has one process. The planet is getting bigger. Everything else follows from that. The simplicity is seductive. The same psychological pull that makes flat Earth attractive to a certain audience, that makes electric universe theories attractive to a certain audience, that makes any single mechanism explanation attractive when the real answer is complicated, is the pull that keeps expanding Earth alive. The fifth reason, and this is the one most directly relevant to today's doublet, is that real events get attached to the framing in ways that look like confirmation. An earthquake on a mid-ocean ridge happens. The ridge is spreading. The Earth is expanding, therefore the earthquake is evidence of expansion. This is a syllogism with a true premise, a true second premise, and a false conclusion, because the implicit claim that ridges are unbalanced is the unsupported step. But on social media, the syllogism reads quickly. The earthquake is real. The spreading is real. The expansion conclusion gets carried along by the apparent reasoning. People do not stop to ask whether the spreading is balanced by anything else, because the framing does not invite that question. Each new earthquake on a ridge looks like a fresh piece of evidence, when really it is the same evidence the hypothesis has always used, recycled with new geographic specifics. The honest scientific response to all of this is not to dismiss it. Dismissal does not work. Saying, "this is obviously wrong," does not engage with why the framing feels right. Saying, "trust the experts," does not address the underlying intuition that maybe the experts are wrong. The response that works is to walk through the evidence slowly, in detail, naming each step, To say yes, the continents do fit on a smaller globe, that visual is real. Yes, the seafloor is spreading, that is real. Yes, you have been told things in textbooks that turn out to be more complicated than the textbooks made them sound. And then to walk through the satellite geodesy, and the subduction rates, and the paleomagnetism, and the energy budget, and the rotation, and the Wegener fit, one at a time, and to acknowledge that the hypothesis was a reasonable thing to wonder about in 1956, and to show, with specific measurements, why the evidence has moved on. That is the response. That is the part where you spend the time to engage rather than to dismiss, because the people circulating Expanding Earth are not, in most cases, malicious. They are working from real intuitions about real observations. They have not seen the counter-evidence laid out clearly. They have seen the original framing and have not seen the refutation in the same place. The remedy for that is exactly the kind of thing that this video has just done. Walk through the evidence, name the names, tell the history, show the measurements, connect each piece back to the central question, and then let the audience decide. Today's doublet on the Southeast Indian Ridge is exactly the kind of news event that gets pulled into bad framings. A real earthquake, a real plate boundary, a real spreading ridge, a viral framing waiting to attach itself. The doublet is real. The expansion framing is wrong. Getting that distinction right matters, because it is the difference between learning something true about how the planet actually works, and learning something false that feels true because it has an image attached to it. Part 11. The other stories that get attached. The Expanding Earth. Hypothesis is the most striking viral framing attached to yesterday's doublet, but it is not the only one. There are 3 other alternative explanations that have shown up in the conversation around this event, and each one deserves a quick, honest engagement before we move on. The pattern of engagement is the same in each case. Name the claim, find the part of it that has a real grain of truth, show where the framing goes wrong. The first alternative framing is the magma causes quakes claim. This claim argues that mid-ocean ridge earthquakes are caused by rising magma rather than by tectonic stress on faults. The grain of truth in this is real. Mid-ocean ridges absolutely are places where magma rises from the upper mantle to create new ocean crust. The ridge axis is literally the place where molten rock is reaching the seafloor, cooling, and being added to the plates. Without magma, the ridge would not exist. On geological timescales, magma is what makes ridges go. So the framing has the right physical process at the right place. The problem is that the framing applies the magma process to a kind of earthquake that is not actually a magma-driven event. The doublet yesterday was not caused by rising magma. It was caused by 2 adjacent fault patches releasing accumulated tectonic strain through strike-slip motion. The signature of a magma-driven earthquake is distinctive. You see clustered swarms of many small events rather than isolated large ones. You see harmonic tremor in the seismic record, a low-frequency continuous shaking that reflects fluid flow through cracks. You see surface evidence of volcanic activity nearby. The doublet has none of these features. It has the impulsive, high-frequency waveform characteristic of a single brittle fault rupture. The 2 events look like transform fault ruptures because they are transform fault ruptures. Magma drives the spreading on the ridge axis, but it does not drive the strike-slip events on the transform faults that offset the ridge segments. The 2 processes are physically distinct, even though they happen in the same general region. The second alternative framing is the connected global cascade claim. This claim argues that earthquakes around the world are coupled, that what happens on one fault triggers events on faults thousands of kilometers away, and that the doublet plus other recent events represents a planetary scale cascade. The grain of truth in this is also real. Dynamic stress triggering, where the seismic waves from a large earthquake briefly stress distant faults, has been documented in the peer-reviewed literature. The 1992 Landers earthquake in California did trigger small earthquakes hundreds of kilometers away. The 2004 Sumatra megathrust did produce small tremor activity on faults in Alaska and elsewhere. Remote dynamic triggering is real, but remote dynamic triggering is a small effect that acts on faults that are already close to failure, and it produces small earthquakes, not large ones. There is no peer-reviewed evidence for global cascades of large events. The Marchitelli paper from 2020 in Scientific Reports examined the possible correlation between solar activity and global earthquake rates, and found a weak statistical relationship that does not rise to the level of a causal mechanism. The Mizuno Kawameno paper from Kyoto in 2026 examined the proposed capacitive coupling mechanism by which solar activity might trigger seismicity, and disconfirmed it under quiet geomagnetic conditions, which is the regime we have been in for the past week. The KP index during the doublet was around 2 to 3.7, well below any G1 storm threshold. There is no temporal alignment between solar activity and the doublet. There is no mechanism that would couple the doublet to other recent earthquakes in the Aleutians or in Tonga, or in the Nazca subduction zone at the energies involved. Each of those events has its own local mechanism. They are not parts of a single global cascade. They are independent events that happen to be in the same week of the catalogue. The HAARP energy budget argument is the cleanest way to dismiss the man-made global trigger version of this framing. The High-Frequency Active Auroral Research Program in Alaska is sometimes cited as a possible global earthquake trigger. The total electromagnetic power that HAARP can radiate is about 3.6 megawatts. The seismic energy released by a single magnitude 6.0 earthquake is on the order of 10 to the 13th to 10 to the 14th joules. To deliver that much energy to a fault patch on the other side of the planet in concentrated form would require HAARP to run continuously at full power for something like 10 billion times longer than the duration of any actual experiment, and would require focusing the energy with a precision that radio waves at HAARP's frequencies are physically incapable of providing. The energy budget is off by 15 orders of magnitude. This is not close to possible. The HAARP global trigger framing is one of the things that gets dismantled the same way every time, and it gets dismantled because the physics is not ambiguous. The third alternative framing is the tsunami warning suppressed claim. This claim argues that no tsunami warning was issued for the doublet, because authorities are hiding the danger. We addressed this earlier in the video, but it is worth restating in the context of the alternative framings discussion. The reason no tsunami warning was issued is purely mechanical. The Pacific Tsunami Warning Center, the National Tsunami Warning Center, and the various regional tsunami centers all use automated thresholds based on the focal mechanism of every earthquake. A strike-slip event on a transform fault does not displace water vertically, and the warning system therefore does not issue a tsunami alert. The same logic that did not issue a warning yesterday also did not issue one for the October 2025 MW 6.0 event on the same ridge, for the May 2026 MW 5.9 event, or for the much larger Macquarie Ridge events of 1989 and 2004. Strike-slip events on oceanic transform faults do not produce tsunamis. There is no suppression. There is no concealment. There is no political decision involved. The physics determines the warning, and the physics yesterday said no wave. There is a fourth framing that shows up occasionally in this kind of discussion, and it is worth addressing briefly because it has been a recurring topic on this channel. The framing is the solar seismic claim, the idea that solar activity, geomagnetic storms, coronal mass ejections, or general space weather conditions are causing the earthquakes we see at the Earth's surface. The framing has been examined seriously in the peer-reviewed literature. Marchitelli and colleagues published a paper in 2020 in Scientific Reports that looked at the statistical relationship between solar activity proxies and global earthquake rates over decades of data. The paper found a weak statistical correlation, but the correlation was not strong enough to support a causal mechanism, and the authors were careful to characterize their finding as a possible weak signal worth further investigation rather than as evidence of a real coupling. Subsequent work, including the Mizuno Kawameno paper from Kyoto in 2026, examined the specific mechanism that had been proposed to explain the Marchitelli correlation, which involved capacitive electrical coupling between the magnetosphere and faults at depth. Mizuno Kawameno tested the capacitive coupling hypothesis against the data and found it disconfirmed under quiet geomagnetic conditions, which is the regime where most earthquakes happen. The space weather situation around yesterday's doublet was quiet. The KP index, which measures global geomagnetic disturbance, was in the range of 2 to 3.7 for the 24 hours surrounding the events. That is below the G1 minor geomagnetic storm threshold, which sits at KP5. The largest solar flare in the 24 hours before the doublet was a C-class event from the active region designated 4446, peaking at 12:16 Coordinated Universal Time, about 2.5 hours before the first earthquake. C-class flares are common and do not produce significant space weather effects on Earth. Solar wind speed was modest, in the 350 to 425 km per second range, which is normal background. The greater than 10 million electron-volt proton flux was at background levels. There is no temporal alignment between any significant solar event and the doublet. The proposed solar seismic mechanism, even if it were real, would require a much larger geomagnetic disturbance to operate, and the actual conditions yesterday were not those conditions. The HAARP energy budget argument also bears on this framing. HAARP is sometimes invoked as a possible source of human-induced earthquakes, on the grounds that a sufficiently powerful electromagnetic transmitter might be able to remotely influence faults. The arithmetic does not support this. HAARP can radiate about 3.6 megawatts of electromagnetic power. The energy released by a single magnitude 6 earthquake is on the order of 10 to the 13th or 10 to the 14th joules. The ratio between those two numbers, when you account for the duration of a typical HAARP experiment and the propagation losses that would attenuate any electromagnetic signal by enormous factors over global distances, is on the order of 15 orders of magnitude. The number is so large that no plausible mechanism of energy coupling could close it. HAARP is not capable of triggering earthquakes at fault patches halfway around the world. The physics says no, and the physics says no by such a wide margin that there is no ambiguity to engage with. These three alternative framings, plus the solar seismic and HAARP versions, all exist in the same general media ecosystem as the expanding Earth framing, and they get mixed together in various combinations on social media. The pattern is always the same: a real grain of truth, scaled up beyond what the evidence supports, attached to a current event as supposed confirmation. The remedy is also always the same: find the grain of truth, acknowledge it, walk through where the framing exceeds the evidence, and show what the actual science says. The doublet did not need any of these framings to be interesting. The actual story of the doublet, 2 fault patches on a transform offset of the southeast Indian ridge, releasing their accumulated strain in 11 minutes, is more than enough. Part 12. The Bigger Plate Boundary Story. The southeast Indian ridge does not exist in isolation. It is one segment of the global mid-ocean ridge system, and at its eastern end it connects to a more complex geological neighbourhood that is worth understanding because it puts the doublet in a larger context. East of the doublet location, the southeast Indian ridge approaches a feature called the Macquarie Triple Junction, the place on the seafloor where the Australian plate, the Antarctic plate and the Pacific plate all meet. 3 plates touching at a single point. The seafloor in that region has a more complicated structure than the simple, ridge-transformed geometry that dominates the rest of the southeast Indian ridge. There are ridges, transform faults, fracture zones, and sections of the boundary that are starting to show subduction behaviour. The Macquarie Triple Junction is, in geological terms, a young feature, and its history is still being worked out by the scientific community. The plate boundary continues east and northeast from the Triple Junction as the Macquarie Ridge, which runs along the eastern side of New Zealand's southern coast and out into the Pacific. The Macquarie Ridge is a strange feature. It is mostly an oceanic transform, like the transform faults on the southeast Indian ridge, but it has some components of transpression, meaning some compression has been added to the strike-slip motion. The result is that the Macquarie Ridge produces some of the largest oceanic strike-slip earthquakes in the global record. On the 23rd of May, 1989, the Macquarie Ridge produced a magnitude 8.2 earthquake. That event was one of the largest strike-slip earthquakes ever recorded. The rupture extended over 220 kilometers of fault in a bilateral pattern on a near-vertical fault plane. The earthquake reactivated a 175-kilometer section of the fault that had been dormant since at least 1964. Anderson's 1990 paper in Geophysical Research Letters documented the event in detail. The aftershock sequence was remarkably small for an earthquake of that size. There were fewer aftershocks on the main fault plane than is typical for a major rupture, which is a characteristic feature of oceanic strike-slip events. The Bath's law expectation that the largest aftershock should be about a magnitude unit smaller than the main shock was not violated, but the total number of aftershocks was unusual. The Macquarie Ridge produced another major earthquake in 2004, a magnitude 8.1 strike-slip event, this time about 200 kilometers to the west of the plate boundary, in what was interpreted as an intraplate rupture inside the Australian plate, rather than on the boundary itself. The 2004 Macquarie event happened 3 days before the December 26th Sumatra megathrust earthquake, which was a magnitude 9.1 to 9.3. The temporal coincidence between the two events has been noted in the seismological literature, and there has been some discussion of whether the Macquarie event might have dynamically influenced the Sumatra event through remote stress transfer. The general conclusion has been that no clear causal connection has been established. The two events were probably independent, with the temporal proximity being coincidental, but the question gets raised because both events were unusually large and they were close together in time, and seismologists are paid to ask whether things are connected. What this broader plate boundary picture tells you is that the Southern Ocean is not geologically a quiet place. It produces large earthquakes. It has been producing them for as long as the plate boundaries have been active. The reason most of the public does not know about the seismic activity in this region is that the events almost never make headlines, because they happen in places where there is nothing to be damaged and nobody to be hurt. The Macquarie Ridge magnitude 8.2 of 1989 is one of the largest strike-slip earthquakes in the global record. Almost nobody outside of professional seismology has heard of it. The Macquarie Ridge magnitude 8.1 of 2004 happened in the same week as the Sumatra megathrust, and it was completely overshadowed by the deadlier event. The plate boundary system that includes the Southeast Indian Ridge, the Macquarie Triple Junction, and the Macquarie Ridge produces seismic activity at a level that, if it were happening on any populated coastline, would be one of the world's most studied tectonic regions. Because it is happening at sea, in the cold ocean between Australia and Antarctica, it is one of the least followed regions on the planet. Yesterday's doublet sits inside that picture. It is a smaller event than the Great Macquarie Ridge ruptures of 1989 and 2004. It happened a few hundred kilometres west of the Macquarie Triple Junction, on the Southeast Indian Ridge proper, rather than on the transpressional Macquarie Ridge structure. But it is part of the same broad plate boundary system, and it reflects the same overall stress regime. The Australian plate is moving north relative to the Antarctic plate at about 70 millimetres a year. That motion has to be accommodated somewhere. Most of it is accommodated by spreading at the ridge axis. Some of it is accommodated by transform faults offsetting the ridge segments. The transform faults release their stress as earthquakes, and yesterday 2 segments of one of those transform faults released their stress within 11 minutes of each other. The deeper history of this plate boundary is worth a short detour, because it helps explain why the Southeast Indian Ridge has the structure it does. The Australian and Antarctic continents were not always separated. For most of the Mesozoic, they were joined together as part of the supercontinent Gondwana, along with India, Madagascar, Africa, and South America. Gondwana started breaking up around 180 million years ago, but the separation of Australia from Antarctica was one of the later events in the breakup sequence. The rifting between the two continents began around 80 million years ago, slow at first, accelerating through the Cenozoic and reaching modern spreading rates around 40 million years ago. The Southeast Indian Ridge in its current form has been the active boundary between the two plates for about 30 million years, since the Oligocene epoch. Before that, the boundary geometry was different, with different segment lengths and different transform fault patterns. The Australian continent has been migrating northward for the entire history of this rifting. As the seafloor spread between Australia and Antarctica, Australia moved away from the Antarctic continent and toward the equator, eventually colliding with the Sunda Plate and the Pacific Plate at its northern margin, where it remains in active collision today. The northward motion of Australia has been one of the fastest plate motions in the modern record, about 7 centimetres a year. This is essentially the same as the spreading rate at the Southeast Indian Ridge, which is no coincidence. The spreading at the ridge is the northward motion of Australia, viewed from a different reference frame. The ridge is where the motion happens. The seafloor that is being created at the ridge is the new substrate that fills in behind the moving continent. The whole system is one process viewed 2 ways. The Antarctic plate, meanwhile, has been relatively stationary in absolute terms over the same period. It sits at the South Pole, surrounded on most sides by mid-ocean ridges, and it does not have anywhere obvious to go. The plate boundary at the Southeast Indian Ridge is, from the Antarctic side, the place where new crust is being added to the southern edge of the world's spreading system. From the Australian side, it is the place that has been pushing the continent toward the equator for tens of millions of years. From the doublet's perspective, it is one stretch of the transform fault system that connects 2 adjacent ridge segments, both of which are part of this much longer process. This is the geometry within which yesterday's 2 earthquakes happened. 2 patches of a transform fault. One ridge segment to the north of the fault, one ridge segment to the south, both ridge segments spreading at about 70 millimetres a year. the transform fault between them accommodating the geometric offset by sliding the two plates past each other in a strike-slip motion. Strain accumulating on the fault patches over decades to centuries, two patches reaching failure within 11 minutes of each other on May 27, 2026. Two ruptures recorded by global seismic stations, two entries in the USGS catalogue, one viral framing attached to those entries, one quiet correction of that framing offered by the actual science. There are about 40,000 earthquakes magnitude 4 or larger reported in the USGS catalogue every year. Of those, around 100 to 130 are magnitude 6 or larger. Of those magnitude 6 or larger events, the great majority happen at subduction zones around the Pacific Ring of Fire. A smaller fraction happen at continental transforms and at continental collision zones. An even smaller fraction happen on oceanic transform faults at mid-ocean ridges. Yesterday's doublet was two of those mid-ocean ridge events, on the same day, at essentially the same point with the same magnitude. It is a small contribution to the year's seismic statistics, but it is a high information contribution. It tells us something about how the system at the edge of Antarctica is segmented and how it releases its stress. It gives us a clean example of a doublet that future seismological papers may use as a case study. And it gives us today a reason to talk about how ridges work, what doublets are, why no tsunami warning was needed, and what the viral framing got wrong. The larger Australian plate boundary, more generally, is one of the most active in the world. To the north of Australia, the plate is colliding with the Sunda plate and the Pacific plate, producing the seismic activity that we see in Indonesia, in the Banda Sea, and in Papua New Guinea. Yesterday's catalogue included earthquakes from all of these regions, a magnitude 5.1 near So, Indonesia, a magnitude 4.8 off Mindanao in the Philippines, a magnitude 4.8 near Finschhafen in Papua New Guinea. These are all related in the general sense to the same Australian plate motion that drove the doublet. The plate is moving. Its boundaries are releasing strain. The earthquakes are the visible record of that motion. To the northeast of Australia, the plate boundary runs through the Tonga-Kermadec Arc, where the Pacific plate is being subducted beneath the Australian plate. The catalogue included a magnitude 5.3 earthquake near Tonga yesterday, and a magnitude 5.3 in the Fiji region. These are subduction-related events, the kind of earthquakes that the expanding Earth hypothesis pretends do not exist, because they are exactly the kind that consume Pacific crust at the rate that balances the spreading at the Southeast Indian Ridge and elsewhere. While the doublet was being recorded on one side of the Australian plate, the subduction zone on the other side was consuming crust at almost the same rate. That is what the global plate budget looks like in real time, spreading on one side, subduction on the other, net surface area change, 0. Every earthquake in the catalogue yesterday is consistent with this picture. The doublet is part of this larger system. It is not a special event hinting at a planetary scale change. It is a moderate-sized release of accumulated strain on one segment of one plate boundary, happening at the same time as other moderate-sized releases of accumulated strain on other plate boundaries around the Australian plate, all of which together add up to a normal week in the global earthquake catalogue. The Australian plate is moving. It has been moving for tens of millions of years. The seafloor at the edge of Antarctica releases its stress every so often. Yesterday it happened to release it twice in 11 minutes. Part 13. What two identical quakes actually tell us. So what does the doublet actually tell us? Now that we have walked through the location, the mechanism, the rarity of the timing, the absence of tsunami threat, the larger plate boundary context, and the long detour through the expanding Earth hypothesis and its falsification. What is the takeaway? What can you actually say about two magnitude 6 earthquakes 11 minutes apart at the same coordinates on the Southeast Indian Ridge? There are 3 viable interpretations, and I want to put them on a spectrum so that you can hold them all in mind without picking too confidently between them. The first interpretation is the most ordinary. The doublet was routine ridge transform seismicity. 2 adjacent fault patches were close to failure for ordinary reasons of accumulated strain. The first one ruptured first, the second one ruptured second, because the first one's stress transfer pushed it over the edge. The 11-minute gap is on the short end of what you would expect from this mechanism, but it is not impossible. The equal magnitudes are consistent with 2 patches of similar size and stress state. The whole thing is the kind of event that happens on transform faults on a steady, low-rate basis, and the only reason this particular case is getting attention is that it is unusually clean as a doublet. Under this reading, the doublet is a textbook illustration of how mid-ocean ridge seismicity works, and nothing more. This is the most parsimonious explanation, and it is probably the right one. The second interpretation is a little more interesting. The doublet might reflect local segmentation of the transform fault into approximately equal-sized blocks separated by smaller obstacles or stepovers. Under this reading, the stretch of fault that ruptured has a specific geometric structure, and the two patches that broke yesterday are typical members of that structure. There may be other patches of similar size on the same fault, also accumulating strain, also somewhere in their failure cycle. The doublet is then a glimpse into the segmentation of the local fault system. It does not tell us anything about a longer-range process, but it does tell us something about how the fault is built, which is the kind of detail that is hard to observe in any other way for a remote oceanic fault. Under this reading, the doublet is a small contribution to the geophysical understanding of this particular plate boundary. The third interpretation is the most speculative, and I want to flag clearly that it is the least supported. There is a possibility that the doublet reflects accumulated stress along this stretch of the southeast Indian ridge that might signal an elevated probability of further moderate seismicity in the surrounding region over the coming weeks to months. There is some published seismological work on long-range stress propagation along ridge systems, including the Antonioli, Cocco, Das and Henry paper on dynamic stress triggering during the 1998 Antarctic plate earthquake. But the published work generally finds that the relevant timescales are days to years rather than minutes. So the 11-minute gap of yesterday's doublet is more naturally explained by the first two interpretations than by long-range stress propagation. The third interpretation is worth flagging only because seismic monitoring of this stretch of ridge over the coming weeks is a reasonable thing to do, given that the doublet happened. But you should not lean on this interpretation. The first interpretation is much more likely, so put it together. The doublet is most likely a routine ridge transform stress release event. It is interestingly clean as a doublet, which makes it worth talking about. It tells us something about the local segmentation of the southeast Indian ridge transform faults. It does not, under any reading, support extraordinary claims. It does not imply that Antarctica is about to split. The Antarctic plate is not in danger of fragmenting. The doublet was on a transform fault offsetting the spreading ridge, which is the most ordinary kind of feature in plate tectonics, and the rupture is consistent with the slow, steady spreading that has been happening for tens of millions of years. It does not imply that a major tsunami is about to hit any coastline. The mechanism was strike slip. The seafloor moved sideways rather than vertically, and no large water displacement occurred. The tsunami warning system did not issue a warning because there was nothing to warn about. It does not imply that the Pacific Ring of Fire is about to go off. Each major earthquake-prone region has its own local stress regime, and there is no peer-reviewed evidence for global cascades of large events from a single trigger. The doublet is not connected to other recent activity in the Aleutians or in Tonga, or in the Nazca subduction zone in any causal sense. It does not imply that a megathrust earthquake is imminent. The southeast Indian ridge is not a megathrust setting. It is a divergent boundary with transform fault offsets, and it produces strike-slip earthquakes in the moderate magnitude range, not megathrust earthquakes. The largest events on this plate boundary system are the strike-slip ruptures on the Macquarie Ridge, which themselves are not the same as a megathrust, and it does not imply that the Earth is expanding. The Earth is not expanding. The radius is stable at the millimetre per year level of measurement precision. The spreading at the southeast Indian ridge is balanced by the consumption of Pacific crust at the Aleutian Trench and the Japan Trench and the Tonga-Kermadec Arc. The total surface area of the planet is conserved. The Pangaea fit on a smaller globe is a coincidence of geometric closure that has nothing to do with a smaller planet. Wegener was right in 1912. The continents drift on a fixed-size Earth, and the visual fit you see on a smaller globe is also achievable on a normal-sized globe once you correctly reconstruct the geometry. The doublet is plate tectonics working exactly the way plate tectonics is supposed to work, nothing more. What the doublet does imply is something quieter and, in its own way, more interesting. It implies that the seafloor between Australia and Antarctica is alive, that the strain accumulating on its transform faults is real, that every so often, on a timescale of decades to centuries, that strain releases in a moderate magnitude rupture, that the system is one of the slowest clocked tectonic systems on the planet, but it is still ticking, and the ticking is consistent, and yesterday 2 ticks happened to land within 11 minutes of each other. The seafloor in one of the most remote places on Earth, where no human has ever stood, where no instrument has ever sat directly above the rupturing fault, where everything we know comes from waves travelling through the deep Earth to recording stations 1,000 kilometres away, is still moving, still releasing its energy, still doing the slow work of the planet, whether anyone is watching or not. There is one more thing worth saying before the final note, and it is about the detection picture, the question of what we actually have the instruments to see and what we do not. The doublet was detected because the global seismic network is good enough to pick up the waves from a magnitude 6 earthquake essentially anywhere on Earth. The location estimate was good enough to put the events at the same coordinates within the resolution of the catalogue. The magnitude estimate was good enough to confirm that the two events were essentially the same size. None of this would have been possible 50 years ago. The global network has grown enormously since the 1960s, when continental drift was being confirmed and seafloor spreading was being mapped. Modern seismology gives us a picture of what is happening on the planet's surface that is, in absolute terms, extraordinarily detailed compared to what was available even one generation ago. But the picture has gaps. There are no ocean bottom seismometers near the doublet location. There are no permanent geodetic stations on the southeast Indian ridge crust. There is no real-time strain measurement at the depth of the rupturing faults. The detail we have on the doublet is what the global teleseismic network can provide from a long distance away. The detail we do not have, but that would be possible with instruments closer to the source, includes things like the precise rupture history of each event, the exact dimensions of the fault patches that ruptured, the actual depth distribution within the upper crust, and whether there were small foreshocks too small to detect from 1,000 kilometres away. Whether such foreshocks existed in the hours before the first event is something we will probably never know. They may have happened. They may have been audible to instruments closer to the source. From where the instruments actually were, they were below the detection threshold. This detection gap is not unique to the southeast Indian ridge. It applies to every remote oceanic region. The Pacific Antarctic ridge, the Mid-Atlantic ridge in the South Atlantic, the Central Indian ridge, the Carlsberg ridge, all suffer from the same instrumentation thinness. The earthquakes happen, they are released, they propagate as waves through the planet, and they are picked up by the distant land-based network, which gives us location, magnitude, and approximate timing. Anything finer than that requires instruments closer to the source, which mostly do not exist. The doublet is, in this sense, a typical case of what we can and cannot see at the edges of the modern seismological picture. There is an interesting consequence of this, which is that the global earthquake catalogue is biased toward the regions where the instrumentation is densest. Japan, California, Chile, Italy, Indonesia, all heavily instrumented, with very low detection thresholds and very precise location capabilities. Other regions, including most of the world's mid-ocean ridges, are detected adequately for large events, but with diminishing precision for smaller ones. This bias affects how we perceive the global pattern of seismicity. Earthquakes in heavily instrumented regions get reported with high frequency. Earthquakes in poorly instrumented regions get reported less. The Pacific Ring of Fire, which is where most of the world's largest earthquakes happen, also happens to be where most of the dense seismic networks are, which compounds the perception. When a large earthquake happens in a less instrumented region, like the doublet at the edge of Antarctica, it can briefly attract attention precisely because it is unusual to see it appear in the catalogue with the prominence that it did. The southeast Indian ridge is doing its work regardless of whether anyone is watching. The plates are moving, the transform faults are accumulating strain. The strain is being released periodically in moderate magnitude earthquakes, on a timescale of years to decades. Yesterday, 2 patches released their stress at the same time. The catalogue recorded both events. The story made it into the news because the doublet pattern is unusual. The viral framing attached itself for the reasons we have already discussed, and tomorrow the cycle continues. The next event on this stretch of ridge will happen when it happens. We will not know in advance. We will not see foreshocks below the detection threshold. We will see the event when it appears in the catalogue, and we will look back at the local stress history to see if it makes sense in context. That is the actual rhythm of how this works, and that in the end is the answer to the question the title posed. The Earth split open twice at the edge of Antarctica yesterday. The cause is not what the viral posts say it is. The cause is 2 adjacent patches of a transform fault on the southeast Indian ridge, both close to failure, both releasing their accumulated strain within 11 minutes of each other, in the most ordinary way that a divergent plate boundary releases its stress. Plate tectonics doing its job, the same job it has been doing for 250 million years, the same job it will be doing 250 million years from now, and on the rare day when it produces something as clean and statistically unusual as a magnitude 6 doublet. We get to look closely, learn something about how the system actually works, and notice that the wrong explanations going around are wrong not because the people offering them are stupid, but because the right explanation is genuinely complicated and the wrong one is shaped to be shared. That is what two identical earthquakes at the edge of Antarctica actually tell us. The planet is fine. The seafloor is doing what seafloors do. The story going viral is wrong, but the actual story underneath it is, in its quiet way, just as interesting. There is no expansion. There is no cascade. There is no hidden danger. There is just plate tectonics, working in the dark, releasing its stress in pairs every once in a while, in places nobody can see, on faults nobody is watching, and being recorded by instruments halfway around the world that pick up the faint pressure waves and write them into the catalogue. The doublet is one entry in that catalogue. The catalogue is the record of how the planet actually works, and the planet works exactly the way the science says it does, even when the viral posts say otherwise. The next time something like this happens, and it will, because the seafloor between Australia and Antarctica keeps moving, and the faults out there keep accumulating strain, the same patterns will repeat. A real event in a remote place, a real explanation from the science, a viral framing scaled up beyond what the evidence supports, and, with luck, a calm walk through the actual story, point by point, that respects both the curiosity of the people asking and the integrity of the answers. That cycle is part of what it means to follow the planet honestly. The science is on our side, the planet is on its own schedule, and the seafloor at the edge of Antarctica will release its next bit of accumulated strain whenever it is ready, and we will be watching from 1,000 kilometers away, the way we always have been and the way we always will be.